Hi, everybody. I'm Greg Fishel, and welcome to bonus weather video number 2 for this week. And we're going to talk about something called the 540 line. If you're a weather enthusiast, and especially if you've been around for a while like I have, you may have heard this term. But if you haven't, we're going to talk a little bit about it today. And basically, we're going to ask ourselves these questions. What is it? What does it tell us? And is it still useful? So here we go. First, some review and definitions. The thickness or the distance between two constant pressure surfaces. Okay, so if you imagine a layer or a surface, if you will, where everywhere along that surface it has the same pressure. So it's not going to be flat, it's going to be undulating like this, okay? But everywhere along that surface the pressure is exactly the same. So the distance between two constant pressure surfaces is proportional to the average temperature of the layer between them, which sort of makes sense, right? Because you think of cold air as being dense and warm air as being less dense. So if you have two surfaces close together and the distance is short, it's going to be cold air, and if they're farther apart like this, it's going to be warmer air, okay? So sort of it fits intuitively. The 540 line refers to the thickness between the 1,000 millibar surface and the 500 millibar surface. Now, the 1,000 millibar surface is usually fairly close to the ground, at least, if you're relatively close to sea level, and the 500 millibar surface is around 18,000 feet. So a contour line on a weather map that's labeled 540 means the thickness along that contour line is 5,400 meters. We just leave that last zero off for convenience. And the 540 line was widely used for years as a good approximation as to where the rain-snow line would be. And so if you were above 540, you were probably going to get rain. If you were below 540, you were probably going to get snow or perhaps some other frozen type. So I had a humbling personal experience, which I still have nightmares about to this day. I'm just kidding, but I did learn a lot this night. So January 19th, 1978, I was in the middle of my junior year at Penn State, and I was forecasting the weather for a radio station in Baltimore, Maryland. They were actually paying me a very nominal fee to do that for them, and it was tremendous experience. It was WCAO radio in Baltimore, Maryland, for those of you that may have lived in that area at one point and might remember those call letters. But anyways, January 19th of 1978, this storm from the south is approaching Baltimore. The 1,500 millibar thickness is forecast to be 543 at the onset of the precipitation around 7 p.m., and it's forecast to rise to about 548 overnight as the precipitation continues to fall. So, we talked about 540 being the boundary, right? So, 543 starts off, goes up to 548. This is a no-brainer, right? Should be all rain. Well, about 8 o'clock that evening, I was in my apartment, and a friend of mine from the Weather Observatory at Penn State gave me a call, and he said, "Greg, I thought you'd be interested to know that at Wallops Island, Virginia, the visibility is 1/16th of a mile in heavy snow." And I said, "Look, I've got a test tomorrow. I've got to study. I'm not in the mood for jokes, okay? Just leave me alone." He said, "Greg, I'm serious." I ran into the observatory, saw that it was snowing to beat the band, not only at Wallops Island, Virginia, but at Baltimore and Washington and Dulles Airport, west of D.C. And so I was scrambling. And so I had to call the radio station and update them, and I think I probably had to update it 2 or 3 times. That I said, "Well, you'll get a couple inches, then it'll change over." And then once 2 was on the ground, "Well, you'll get a couple of more, 4 inches, and then it'll change over." And then it finally got to 5 to 7. So it continued to snow into the wee hours of the morning and finally turned over to freezing rain and sleet and pretty much ended that way. The observed thickness when they launched the weather balloon from Dulles Airport in Virginia at 7 p.m. was 543. The forecast was right on the money. And at 1 a.m., the observed thickness was up to 547. So the forecast of the thickness wasn't bad. So how did it snow? Well, the upper part of this 18,000-foot layer from 1,000 millibars to 500 millibars was unusually warm. It was like minus 13 degrees Celsius, which is about 9 or 10, okay, Fahrenheit. At 18,000 feet, in the wintertime, that's warm, warmer than normal. But that warmer than normal layer up there elevated the thickness value to a deceivingly high number. And it didn't matter because even though it was unusually warm up there, that part of the atmosphere is almost always cold enough to snow anyways, okay? So it's sort of irrelevant, the fact that it was unusually warm at 18,000 feet. So 18,000 feet is way too deep of a layer to examine when you're trying to figure out whether or not it's going to rain or snow, because a good part of that layer, almost half of it, it's always cold enough to snow. So we started looking at thinner layers that were closer to the surface. And now the 1,850 millibar thickness and the 850 to 700 millibar thickness are the most widely used now to get an estimate as to where these various boundaries are going to be. So let's take a look at this graphically now. So we have our four surfaces of constant pressure: 500 millibars, 700 millibars, 850 millibars, and 1,000 millibars. And the heights of these, again, they vary, but approximately 18,000 feet, 10,000, 5,000, and then close to the surface. So up at this, close to the top of the layer, up close to 18,000 feet, it was warmer than normal. But who cares? Because, again, it's always cold enough to snow up there anyways. The thicknesses now we look at on a daily basis, or at least when we're concerned about a winter weather threat, are the 850 to 700 and the 1,000 to 850. And in this particular case, in Baltimore, Maryland, and Washington and surrounding areas, it was plenty cold enough for snow during that given time. And then eventually, when the thickness did get up to 547, then this layer up in here, the 850 to 700 millibar one, actually went above zero before this one did. And so that's what changed it over to sleet at that particular point in time. But I certainly learned a lesson that night that looking at an 18,000-foot layer is simply too broad, and you've got to look at the details. Even if you look at these layers down here, you know, that are closer to the ground, the temperature can still be distributed very differently. Like you may have an average temperature in a layer of 32, but you could have that with a temperature of 26 at the top of the layer and 38 at the bottom, or you could have it 38 at the bottom and 26 at the top. You still get the same average, okay? So the way the temperature is distributed in a given layer is really critical in terms of whether or not you end up getting one form of precipitation or another. All right, I hope that makes sense, and takes me back to some good old days back at Penn State. Even though it was a humbling forecast, it was a learning experience, and I always had a lot of fun learning. Okay, that's it for now. You all have a wonderful weekend, and we'll talk to you again on Monday.